Hi, today we're looking at methods of trigonometric substitution. And there are a few cases where these methods of trig substitution come about. The first one of these is when you see something like a squared minus x squared sitting inside of an integral somewhere, which we have right here in this problem. This is a number squared minus x squared. The other cases that we're going to be looking for are x squared minus a squared and x squared plus a squared. So these are really, again, the three cases that we're going to be looking for here today. So what we're really going to do is take advantage of some of our trigonometric identities. And for a problem like a squared minus x squared, we're going to be using a substitution. X is a sine theta. So in this case, our a would be 5, because 5 squared is 25. So we're going to make the substitution that x is 5 sine of theta. So we need to go ahead and find dx. Well, dx would be 5 cosine theta d theta. Well, what happens if we do this substitution? The square root of 25 minus x squared becomes the square root of 25 minus 25 sine squared of theta, which, because sine squared theta plus cosine squared theta is 1, then this particular thing becomes 25 cosine squared of theta, just using that Pythagorean identity kind of in reverse. So the nice thing that does for us then is that it's something we can actually take a square root of, and we get 5 cosine theta. So if we go back to our original integral, we were integrating basically 1 over square root 25 minus x squared. So now we replace dx with 5 cosine theta d theta. We've now figured out that the bottom also works out to 5 cosine theta d theta. Let's come back to this in just a second. So we really just end up integrating 5 cosine theta over 5 cosine theta d theta, which means we're integrating 1. So that part's really easy. The issue then becomes figuring out the bounds. Well, if we take a look back here, we had set this up so that x was 5 sine of theta. So that means that sine of theta is x over 5. So when we had x running from 0 to 5 halves, if x is 0, sine of theta would be 0. Well, that's going to happen when theta is 0. And if x is 5 halves, then 5 halves over 5 is 1 half. And the sine of theta is 1 half at pi over 6. So we're going to end up integrating 0 to pi over 6, this 1, and that's where we get pi over 6. The other thing that you might have seen on the paper here is a little triangle that represents the substitution that we did. So we made sine of theta, 5 sine of theta was our x, which means that sine of theta is x over 5. You can see that here. And then we could figure out the other little side in our triangle. It's the square root 25 minus x squared. Oh, that was actually the original thing that we had in our substitution here. So that becomes more interesting on some of the other problems. We'll see that we draw this triangle in every one. We didn't really need it on this problem. But on we go. Okay. The second problem that we're going to look at this one's not a definite integral, it's just a regular integral. We're integrating dx over 1 plus x squared to the 3 halves. So this is of that form, a squared plus x squared. And for these, we're going to use the substitution x is tangent theta. Okay? So if x is tangent theta, then dx is secant squared of theta d theta. And if we work this out, the dx on the top becomes secant squared theta d theta. Our denominator, we get 1 plus tangent squared theta to the 3/2. Well, 1 plus tangent squared is secant squared. We have that identity. We know that one. So we end up with secant squared over secant squared to the 3/2. Well, secant squared to the 3/2 is secant cubed. And secant squared over secant cubed gives us 1 over secant. So that means we're just integrating cosine theta d theta. So we'd end up with sine of theta plus a constant. So one thing that we could do here, and you might see this answer somewhere, is we could just replace theta with, well, what was theta originally? Theta would be the inverse tangent of x. So we could write this answer as sine of the sine of the tangent inverse of x plus a constant. That's not incorrect, but there's a better way to write that here. We can go back to drawing the little triangle. So our substitution that we made was that x was the tangent of theta. So for the tangent of theta to be x, tangent of theta is the opposite over the adjacent. So we'd want x over 1 here. So x and 1, that would make the hypotenuse here the square root of x squared plus 1. And then we want sine of theta. Well, sine of theta would be the opposite over the hypotenuse. So that is exactly x over square root x squared plus 1. So and our final way that we could write this is x over square root x squared plus 1 plus a constant. So pretty nifty little use of trigonometry in this substitution. The last one that we're going to look at is one of these of the form x squared minus a squared. And this time we're going to use an x equals secant theta. A secant theta substitution. So here we did x is 11 secant theta. Again, because that's our a squared right there. So dx becomes 11 secant theta tangent theta. Well, when you do this substitution here, we're getting 121 secant squared of theta minus 121. Well, again, we're back to the same Pythagorean identity that we were using before. So we're using this identity, but this time we're moving the 1 to the other side to say secant squared minus 1 would be tangent squared. So for us this time, we're going to end up with, this would be 121 tangent squared, and then the square root of that would be 11 tangent theta. Well, that would cancel with the 11 tangent theta on the top, and just leave us with the secant of theta. So actually this 11 is not here. Okay, because the 11's cancel. We had an 11 here, and an 11 came out of this square root. So we get just the integral of the secant of theta d theta. Well, this is an integral that we figured out a couple sections ago, and we have in a table now, is the natural log of the secant of theta plus the tangent of theta plus a constant. These are in absolute values. Well, again, we'd like to rewrite these in terms of x instead of theta. Well, secant of theta is an easy one to rewrite because x is 11 secant theta, so secant theta is x over 11. For the other one, we're going to need to go to the right triangle. If the secant of theta, which is 1 over the cosine, so that's hypotenuse over the adjacent, is x over 11, then hypotenuse is x, adjacent's 11. This would be the square root of x squared minus 121. So then tangent of theta would be opposite over adjacent. That's the other one that we need. So that would be root x squared minus 121 over 11. So we could rewrite this as natural log x over 11 plus square root x squared minus 121 over 11, which you can just share that denominator for those, plus a constant. There's a little bit more cleanup that we can do on this. One of the log rules, if we're dividing by 11, we can rewrite that as subtracting by the log of 11. And then this log of 11 can get absorbed into the constant because it's just another constant. It can get absorbed into the arbitrary constant, and we get that for our final answer. Okay, so to summarize, we went over 3 cases. The first case that we looked at was the case where you have something of the form x squared minus a squared. We do a substitution there, that x equals a sine of theta. And then we use the sine squared plus cosine squared equals 1 identity to simplify things. The next example that we did, we were using something of the form a squared plus x squared. Inside of our integral, we did the substitution x equals tangent theta. And we used the identity tangent squared plus 1 equals secant squared. And then the last substitution that we just did, we had something of the form x squared minus a squared. We did a substitution x equals secant theta. Sorry, there should be a's on these. And we got, again, we used the same trig identity there, except we ended up with it in the opposite form, where we were using secant squared minus 1 was tangent squared. Okay, that is the end of our video for trig substitution, but not the end of our fun with trig substitution.